So the method of stationary phase says that this integral is difficult to compute, but if x, y, and z are large, you find that if x is large, y is large, and z is also large, if you were to make a small change in kx or a small change in ky, the phase would vary rapidly. The phase would vary rapidly. And so if you were to compute this integration over the kx and ky plane, the computation is extremely laborious because what you have is that you have a rapidly oscillating integrand. From this thing and this thing, you gave rise to rapidly oscillating integrand. And it's extremely difficult to compute when x, y, and z are very large. But there is only one yardstick in electromagnetics. What does it mean when x, y, and z are very large? It means that they are very large compared to wavelengths. So this statement is the same as x over lambda, y over lambda, z over lambda becomes very large because we don't have any other yardsticks. The yardstick to measure distance is wavelength. So if your observation point is very far from the source compared to the wavelength, you are far away. You're in a far field region. So let's assume that this to be the case. Then as I said before, the integrand is going to be rapidly varying. Okay, so if I were to look at the integrand, it will look something like this. Like say if I look at the function like if I look at this function, let me see, if I call my g kx, ky, lambda. Lambda is a large parameter. And if I call this to be this function, e to the ikxx plus ikyy plus ikzz, okay, then this function is going to be a rapidly varying function. Let me write my kx properly. Kx is going to be a rapidly varying function of kx, ky, kz, t. T can represent kx or ky. So if I were to plot this function as a function of kx or t, where t can be kx or ky, then this function will be rapidly varying. Okay, if we to change t by a little bit, the phase would change, which means that most of the contribution to this integral would come from the part where the phase is the least rapidly varying. So over this part, T naught is when the phase is least rapidly varying. Then you see that the integrand will look something like this. And you can see that the other parts of the integrand will be rapidly varying. The integration will cancel each other. The contribution to the integration will cancel each other, except for the contributions in the vicinity of the stationary phase point. This is called the stationary phase point. Okay, this is called the stationary phase point. Essentially, I'm writing this that this should be lambda ht kind of thing. Okay, so if I looked at this function h of t, which is the thing in the exponent, it is not rapidly varying. It actually varies slowly as a function of t. Only after you multiply by lambda, which can be x, y, and z, which is a big number, then the function becomes rapidly varying. And the contribution to this integration will come from the vicinity of this stationary phase point, where the integrand is least rapidly varying. So the idea of finding the approximation to such integral is to find where the stationary phase point is. Okay, so if I have such a function, and for instance, if I look at my E1z, then I can write it as, let me write it out in full first. Okay, it could be a Sommerfeld integral or Weyl integral. It would be this very, very complicated function multiplied by this exponential function, which can be rapidly varying when x, y, z are large. Okay, let me put in the k1z here. Okay, when x, y, z are large, this thing is rapidly varying, but I can look for the stationary phase point at which this would be least rapidly varying, and you can actually work out the stationary phase point. It's given out in the lecture note, and let me just write down the answer for you. The stationary phase point actually turns out to be very much related to x, y, and z. If you were to re-express this in terms of Cartesian coordinate, the stationary phase point is given by k1 sine theta cos phi. And then kys is given by k1 sine theta sine phi, where theta and phi are related to the x, y, and z coordinate in spherical coordinate. Is, in other words, r is given by r sine theta cosine phi, y is given by r sine theta sine phi, and then your z is given by r cosine theta. Okay, so if you were to express x, y, z in terms of spherical coordinate system, you find that the stationary phase points have a very nice formula given by this. And then what you do then is to evaluate this function. This is slowly varying. Okay, this is slow varying. And you express and approximate this about the stationary phase point by the argument that all the contribution to the integrand will come from this stationary phase point. Okay. And then there should be a k1z somewhere around. There should be a 1 over k1z around here. Okay. So what I'm left with in the integrand then is equal to e to the I kxx plus kyy plus I k1zz over k1z. And this part, I can use back the Weyl identity and say that it becomes like the spherical wave again. Okay, it becomes like a spherical wave again. So you can make this stationary phase point approximation and look at this Sommerfeld integrals and get some physics out of these integrations. Okay, and I will let you read about the details in the lecture notes because I don't have time to talk about the gory details of this thing. Another thing that you should very much bear in mind is the concept of Riemann sheets and branch cards. And if you really want to understand this field, you actually have to understand Riemann sheets and branch cards. The reason why you need to understand Riemann sheets and branch cards because I can give you a very simple example. If you don't have this, these are very important for good bookkeeping. Okay, I can give you an example, and you will probably have to scratch your head as to what's wrong with this proof. I can say that I is the square root of -1, but it's also the same as +1 over -1, and then it's the same as square root of 1 over -1, and hence it's a square root of 1 over I, and then you get I squared. If you multiply again across, you get I squared is equal to 1, you get -1 equal to 1. So this is a puzzle. Okay, why is this the case? Well, I arrive at this because I have very sloppy bookkeeping. I didn't keep track of my square roots. By right, every time I take a square root, I should assume two possibilities. Okay, if I assume all those two possibilities, then I would not have this paradox or contradiction. You can read about this in the lecture notes. As how important it is to have Riemann sheets and branch cuts in order to solve this problem in the unambiguous fashion.